I suspect you know about this. All right, let's finish chapter 18. Finally. Last two considerations. How do we get at pH, hydronium ion concentration? For water solutions which contain Bronsted-Lowry acid-base principal equilibria which do not involve the production of hydronium ion or hydroxide ion. So far regarding this, we've looked at determination of hydronium ion concentration for 0.10 molar sodium bicarb solution, 0.10 molar ammonium cyanide solution, and found out hydronium ion molarity determination for those systems is really not difficult at all. Why so? Because the K value for the principal Bronsted-Lowry acid-base equilibrium reactions in those systems, bicarb solution is bicarb ion plus bicarb ion. Ammonium cyanide solution is ammonium ion plus cyanide ion. The K values for those reactions are very, very large compared to the K values for the equilibria, which in those systems we have to consider to get at the hydronium ion concentration. What did that mean? That means from the reaction bicarb ion plus bicarb ion to make quote-unquote hydrated CO2 plus carbonate ion, the molarities of quote-unquote hydrated CO2 plus carbonate ion compared how? How'd they compare? How did they compare? That underlies why this calculation is not difficult, the calculation of hydronium ion concentration for the sodium bicarb solution. The hydrated CO2 and carbonate ion molarities were equal because the hydrolysis reaction of bicarb ion, which produces hydrated CO2, has a K value that's tiny next to the bicarb ion plus bicarb ion K value. So will the hydrolysis of bicarb in sodium bicarb solution, which results in the production of hydrated CO2 and hydroxide ion, will that reaction contribute to the resultant equilibrium molarity of hydrated CO2? No. And how about the second hydrolysis reaction for bicarb ion, where bicarb reacts with water as an acid and makes hydronium ion and carbonate ion? K value for that is 4.8 times 10 to minus 11. That's Ka for bicarb. How did that K value compare to the K value of the reaction bicarb ion plus bicarb ion? It was tiny next to that. We're just talking about what we did last time. Upshot, that reaction makes no contribution, practically speaking, to the solution concentration of carbonate ion. Consequence, bicarb ion plus bicarb ion making hydrated CO2 plus carbonate ion is a reaction which can be read stoichiometrically. What's that mean? You did stoichiometry in 2045. Did you learn what the word meant? Huh? Many reactions are not stoichiometric. Why not? Why is the reaction of ammonium ion plus bicarb ion for the ammonium bicarb solution, why is that reaction not stoichiometric?
There are additional side reactions.
All right, what's that mean?
After the initial reaction, the products and reactions take place in other reactions. So
I think you got the idea, but you're using too many words. Let's try it this way. There's the reaction which I had mentioned regarding bicarb ion plus bicarb ion. And what did we say? We just said this reaction is stoichiometric. What does that mean? It means if for this reaction we imagine that X moles of bicarb ion reacts with X moles of bicarb ion. Watch out, this is fancy. That means 2X. Okay. What will be the resulting mole quantities of hydrated CO2 and carbonate ion produced by this reaction? What? What? X for each. Right? That's what it means to say a reaction is stoichiometric. You can read it as a direct mole relationship. Okay? And why did that hold for this system? Because the Ka reaction for bicarb has a K value that's tiny next to K for this. And the Kb value for bicarb has a K value that's tiny next to this. So hydrolysis of bicarb as an acid, even though it produces carbonate ion in addition to hydronium ion, does not produce a carbonate ion value which will increase the concentration of carbonate ion produced by this reaction. And hydrolysis reaction of carbonate ion, bicarbonate ion, pardon me, where the bicarbonate ion is behaving as a base. Bicarb plus water makes quote-unquote H2CO3 or hydrated CO2 plus hydroxide ion. Does that reaction produce an increase in the molarity of the hydrated CO2 molarity which is produced by this reaction? Yes or no? No. No. So this reaction is stoichiometric. Same thing for the ammonium cyanide solution. The K value for this reaction, which is 0.90, we calculated it. Of course, we also calculated the K value for the bicarb reaction. The K value for the ammonium ion cyanide ion reaction, which is 0.90, is a very, very large number compared to Ka ammonium ion, 5.6 times 10 to the minus 10, or Kb cyanide ion, which is 1.6 times 10 to the minus 5. See, sometimes it's valuable to have this table memorized. That's all right. You always have the acid-base table and the corresponding information available to you for use on any quiz and exam. As I said, I don't expect you to memorize this stuff, but I do expect you to be able to use it. Upshot, is this reaction equation also a stoichiometric relationship? Can you read it as a mole ratio directly? You're damn right. Because although Kb cyanide is far bigger than Ka ammonium ion, so let's focus on Kb cyanide, where cyanide reacts with water to make HCN and hydroxide ion. Kb cyanide 1.6 times 10 to the minus 5. K for this reaction 0.90. You have the information in your notes. Let it talk to you so you know what it means. The Kb value for cyanide is much smaller than 0.90 K for this reaction, which means the hydrolysis of cyanide ion on production of HCN will still not result in a measurable increase in the solution HCN molarity. Because this reaction is, practically speaking, the only source of HCN in the solution which amounts to anything. So this too is a stoichiometric statement. If X moles of this reacts with X moles of this, I'll make X moles of this and X moles of this. Done. Now what about this system, which we talked about last time also? Ammonium ion plus bicarb ion, which makes quote-unquote H2CO3 plus ammonia. We calculated K for that reaction. It's a very simple task. You write the equilibrium constant, multiply it by hydronium ion molarity over hydronium ion molarity to evaluate K, or by hydroxide ion molarity over hydroxide ion molarity. Either one will allow you to calculate K. And if you compare the K value for that reaction to Ka ammonium ion, because in this solution, what's the principal acid species? The strongest acid species present in high concentration? Ammonium ion. In this solution, what's the strongest base species present in high concentration? Bicarb ion. And Kb bicarb is bigger than Ka ammonium ion. We've already reflected on that. So before you do any arithmetic on this solution, you know it is mildly what? Basic. Bingo. As reflected by the fact that Kb bicarb is a bigger number than Ka ammonium ion. Okay? And K for this reaction is a hell of a lot bigger than Ka ammonium ion or Kb bicarb. So right now you might say, well then, ammonium ion plus bicarb ion making hydrated CO2 plus ammonia is also a stoichiometric relationship. Ha ha! But now you'd be wrong. And why would you be wrong? Well, we have to go back all the time. Never ever forget what property of a chemical system, like a solution, what?
PSI.
PSI! And found out what? What do we find out by looking at the PSI for this system? In addition to the chemistry so far we've discussed, ammonium ion reacting with bicarb ion, ammonium ion reacting with water, hydrogen carbonate ion reacting with water as a base, where we're considering Kb bicarb. What's the other reaction in this system which so far we haven't considered, but which we must consider if you want to calculate the correct hydronium ion molarity for this system? Yeah, remember that? Because bicarb reacts with bicarb also. It all follows from PSI. You got to let the PSI talk to you. Is this tough? You're damn right. Is it challenging? You're damn right. But this is the way chemistry is. Mother Nature doesn't give a damn what we think or what we believe or what we calculate. Mother Nature behaves as Mother Nature chooses to behave. And it's our obligation as students of Mother Nature, that's what chemistry is about, to try to understand how Mother Nature behaves. And if we make a miscalculation, but stand behind it and say, oh, what I did is fine. You think Mother Nature cares? Mother Nature says to you. And it's our job to go back and fix the blunders we made. Because Mother Nature will still behave as Mother Nature behaves, in accord with energy and stability, not ever considering what the hell we think or care or feel. Doesn't care. But we have to care if we want to understand. Ha ha! So, as you have been, I hope by now, browbeaten, kicked, hounded, emphatically reminded by the SOB known as Horvath, you'll pay attention to PSI and let it talk to you. Because if you don't do that, you can't win. But if you do that, you have every chance to win. And that's what we want. Okay. Now then, that's going to obligate us to, for this system, pay attention to material balance and pay attention to charge balance. The relationships for which we wrote last time, I'm not going to rewrite that. And on a quiz or exam, I'd never give you a calculation like this because it takes too much time. But what would I ask you? I'd ask you about the considerations you have to make to do the calculation correctly. That I will ask. I'd ask you to realize all the equilibria of consequence which must be considered. That's a fair question. Again, I wouldn't ask you to go through the calculation itself. That's too much. But knowing how to do the calculation is more important, because that means you understand the chemistry, and that's what we're trying to achieve. Because once we lay down the calculations that need to be done, I can take somebody from high school first-year algebra, they can do the calculations, because we haven't done any arithmetic that's above and beyond the rigors of first-year high school algebra. I mean it, and we won't throughout the whole term. It's not necessary. But what the first-year high school student can't do, I don't believe at this stage of the game, because he or she has not yet been given the appropriate and sufficient background, is to get on with the appreciation of the chemistry of the system. And that's what we're here to do. Now then, one more consideration. I think for systems such as this, which will ultimately allow you to write an equation for which you have solved the system in terms of its principal chemical components to arrive at an expression for the hydronium ion concentration. And in this expression, the only unknown will be the hydronium ion concentration. See this expression? At first glance it looks horrid, doesn't it? Not. This is a simple expression. How many unknowns does this have? One. You can do the same thing with this system. After you pay attention also to, in addition to the principal equilibria, material balance, charge balance. But now you've reduced it to an algebra puzzle, so I let you do that. But, as you'll see in a moment, to solve this, just as in solving the expression you derive at this system for the hydronium ion molarity, let's speculate on a reasonable value for the hydronium ion molarity so we know what test values to try. And for this kind of system, the best way to make a reasonable speculation is to start first by recognizing the boundary hydronium ion molarity values. This we have not yet discussed, if my recollection is correct. It's at the tail end of the notes in Chapter 18, so if you've done your work, you've read about this. But let's have a brief conversation. First, whoops, forgot something. The calculation for the hydronium ion molarity in the 10th molar sodium hydrogen carbonate solution results in this hydronium ion concentration for the sodium hydrogen carbonate solution. So since we discussed that prior to discussing the ammonium bicarb solution, we'll take that as a given. We already have that information as it follows from the analysis of the sodium bicarb solution. Hey, let's always take advantage of what we know. So with that information as a given, I'll ask, since we've recognized this solution to be mildly basic, correct? Because Kb bicarb is a bigger number than Ka ammonium ion. And Ka ammonium ion is a bigger Ka value than Ka bicarb ion. That's how we recognize for this solution ammonium ion is the main acid. For this system, which is mildly basic, what's the upper limit max possible value for the hydronium ion concentration? 1.0 times 10 to the minus 7. You betcha. And I should hope you'd recognize that it's very, very, very likely that the correct hydronium ion molarity for this system is smaller than this. But whatever it is, it cannot be bigger than this. That's impossible. Now let's talk about lower limit hydronium ion molarity. And tell you that the reason why I wrote this up here is because that number is the lower limit hydronium ion molarity for the ammonium bicarb solution. My question to you is do you see why this is true?
Sodium has no effect on pH, but
correct.
ammonium will make it more acidic.
Ammonium ion is a stronger acid than?
Sodium.
Come on, stronger acid than what? Bicarb ion, you betcha. Point. This solution is mildly basic. This solution is mildly basic. But this solution compared to that solution, which of these solutions got to be somewhat more basic? This one. Why? Because here, the principal acid in the system is bicarb ion, right? And that Ka is 4.8 times 10 to the minus 11. But here, the principal acid in the system is ammonium ion. And Kb ammonium ion is 5.6 times 10 to the minus 10. And that's bigger than 4.8 times 10 to the minus 11, right? So the acid species in this system is stronger than the principal acid species in this system, isn't it? That makes this system not as basic as that system. But since both systems are basic, we know this one is basic, but less basic than that one. Point, we now have the boundary hydronium ion molarities. Because whatever the hydronium ion molarity is, the lower limit hydronium ion molarity for this, it can't be smaller than this. Because this is the hydronium ion molarity for that solution. And we know our ammonium bicarb solution, watch out, sounds like double talk. Our ammonium bicarb solution has a hydronium ion molarity which has got to be greater than this because that solution is less basic, or if you wish, more acidic. It's not acidic, but it's more acidic than this solution. Okay? And so, one more. There's the answer for the ammonium bicarb solution if you wish to plow through the challenge of doing the arithmetic, which you should. If you've got a need for scratch paper, come see me and I'll give you a reams of it. How about the hydronium ion molarity for a particularly dilute solution of acetic acid? Have we done some arithmetic on acetic acid solutions previously? Anybody who does not remember that hasn't been here very much. And so far, among the various considerations we have made with respect to our analyses of the acetic acid solutions considered, we have, of course, verified the fact that as the acetic acid solutions are considered at greater degrees of dilution, progressively less concentrated acetic acid solutions, what's happened to the ionization extent of acetic acid in the solutions? It's increased all the time. And now we're looking at an acetic acid solution which is damn dilute. So far, until now, if my memory is right, the lowest concentration acetic acid solution we've considered is 1.0, times 10 to the minus 4. And for that solution, we got an ionization extent of 34%. Well, now we're looking at a solution which is far less concentrated than 1.0 times 10 to the minus 4. Or put a better way, I should think, far more dilute. This stuff is approaching water, pure water. And Ka for acetic acid is 1.8 times 10 to the minus 5. That means, in particularly dilute solution like this, we can well expect the ionization extent of acetic acid to compare how to 50% extent? Greater. So, with that information before me, in addition to recognizing, because this solution is so very dilute, beside this equilibrium constant expression, what other equilibrium constant expression will I need to consider to correctly calculate the hydronium ion molarity for this solution? Here it is. Right? You betcha. And this is more challenging than calculating the hydronium ion molarity for a very dilute solution of a strong acid or strong base. Because for those solutions, the ionization extents are 100%. Here, we don't know. We have to do some arithmetic to find out, because we're looking at a solution in which the ability of the solute acid, acetic acid, to ionize is subject to equilibrium control. Whereas ionization extent of HCl, not subject to equilibrium control, that's 100%. Sulfuric acid, 100%. Of course, with sulfuric acid solution, you still have the problem with wrestling with what? The ionization extent of what? Hydrogen sulfate ion, right? Sodium hydroxide solution, no problem. Ionic compound dissociates into sodium ion, hydroxide ion. And all the dissolved sodium hydroxide is dissociated, at least at low molarities. All right? So let's look at this. And after recognizing that the ionization extent of acetic acid is going to be quite large, let's try 100%. Now, you have to be on your toes with the arithmetic when you try 100%. Because if you take 100% to be an absolute value, then how much acetic acid is left after acetic acid reacts with water? None. So what's the value of this going to be? 0. So this expression is meaningless. So you can't do that. So let's pick on an ionization extent to 3 sig figs, which considered to 2 sig figs is what percent? What's this considered to 2 sig figs? 100%. What if I wanted to refine the calculation with 4 sig figs in my estimated percent ionization? If I wanted my estimated percent ionization to 2 sig figs be 100%, what would it be to 4 sig figs? 99. How about that? Now you might write it as 99.50, but there's a lot of monkey business, arithmetic monkey business, that I want to be bothering with when you have a 5 after the decimal point followed by a string of zeros. Do I round up or do I round down? Well, statistically, half the time you round up, half the time you round down. I don't want to fool with that. So I'll do it this way. Or now I don't have to fool around with this rounding, because this is guaranteed to round to 100% to 2 sig figs. All right? Now then, in trying 99.6%, what am I going to do? Tell me the arithmetic that I'm going to do. Here's all the expressions we need. There's K acetic acid, KW, material balance for acetic acid, and charge balance for the system. A nice simple charge balance expression, because there's only 3 terms contained within, and this is the one we want. And this is really a statement containing how many unknowns? Just 2, because hydroxide ion molarity is this. All right? So if I'm going to try 99.6%, I'm going to take 5.0 times 10 to the minus 7, multiply it by 99.6%. as a decimal fraction, which means 0.996. And that to 3 significant figures, because when you do this arithmetic, you got to do all the steps to 3 sig figs and round back to 2 when you get the end. When you get at the end. That will keep significant figure accuracy preserved. So I repeat my question for this system. 0.996 times 5.0 times 10 to the minus 7 gives you what value? The acetate ion molarity, right? And how will I get the acetic acid molarity? I'll subtract that number from 5.0 times 10 to the minus 7. Okay? And here is the acetate ion molarity, is it not? Right? Acetate ion molarity, rearrange this. So hydronium ion molarity minus Kw over hydronium ion molarity is acetate ion molarity. That's this. I told you this is a simple expression. But if you look at this like nothing but a conglomeration of chemical terms without recognizing what these chemical terms mean, then all that's going to do is give you a headache. You don't want that. You want to look at these things and always ask yourself the question, what the hell does this mean chemically? This is chemistry class, remember that? How could you ever forget? Okay. So you now know the values you'd get for acetate ion and hydronium ion. And at 99.6%, this whole term would become 1.3 times 10 to the minus 4. That's too big, isn't it? That's bigger than 1.8 times 10 to the minus 5. I'm saying all this becomes 1.3 times 10 to the minus 4 trying 99.6%. Okay? So, we got to try an ionization extent that's smaller. So we'll try 96%. This whole term then becomes 1.2 times 10 to the minus 5. So what do I know now? What do I now know? I know that the ionization extent is bigger than this and smaller than this. Right? Pretty small box, don't you think? So, if you do some more work, you'll find out, if I did my arithmetic right, that this comes to be 97.2 or 97.3% right on the nose to 3 sig figs. And that ionization extent value gives you 1.8 times 10 to the minus 5 for this term. Now, tell me, how did we get to hydronium ion molarity? Did you recognize how to get that along the line? The hydronium ion molarity is this term plus this term, is it not? And this we got from this, taking the percent of the m sub I value. Okay? So how do we get the hydronium ion molarity that corresponds to these ionization extents to put in here? Because that's one part of the puzzle we didn't yet discuss. How do we do that? what you need to do, this is on the board. You see this? See this? And where do we get this from? Okay. Ionization extent times m sub I, right? That gives us a number. Speculate on ionization, multiply it times m sub I, plus hydroxide ion molarity. Times hydroxide ion molarity. How many unknowns in that expression? How many? 1. This is just a number. So can you solve this for the hydroxide ion molarity? Yes? If you can solve it for the hydroxide ion molarity, can you get the corresponding hydronium ion molarity? Yes! And now you know how to get the hydronium ion molarity for this. And there you go. Do it! You need the practice. I'm not going to write all this arithmetic on the board for you. You're the ones that need the practice. And I guarantee that practice means you take your pen or pencil and put it to the scratch paper and get going. You can watch a concert pianist play great music forever. You can listen to this great music as the concert pianist creates it forever. Is that going to make a concert pianist out of you? Till you sit in front of that piano and start pounding on the keys, you're never going to be a concert pianist. You can watch somebody paint walls all you want. It's not going to make a painter out of you. You got to put that brush in your hand and get going. Now then, we got a couple minutes. Let's finish with one consideration. Chapter 19. In brief, you have so far recognized from chapter 19 that on occasion you have the liberty to calculate the solubility of a semi-soluble salt in water solution if the ions of the semi-soluble salt show no appreciable acid or base properties. That means the only equilibrium you have to pay attention to is the KSP equilibrium, like silver chloride. Such a calculation is very simple. But most semi-soluble salts are not so chemically simple because most semi-soluble salts contain an anion that's a stronger base than water. So now to get at solubility, in addition to the dissociation equilibrium, like calcium carbonate, because if you take and observe the pH of calcium carbonate saturated solution, how many of you are in the laboratory in assignment 3? Have you done this? Have you observed the pH of saturated calcium carbonate solution? What did you get, roughly? How much? 10. How about that? Does that 10 pH for saturated calcium carbonate solution, is that explained by this chemical expression? Does this have hydronium ion or hydroxide ion in it? Hell no. So what else do you have to pay attention to?
Carbonate with water.
Carbonate and water. We'll pick it up from this point next time.